Continuing with the method of preparation of haloalkanes and haloarenes from hydrocarbons, now we shall consider preparation of aryl chlorides or aryl bromides by electrophilic substitution in presence of halogen carriers like iron or ferric chloride. You have already studied this reaction last year in class 11th under hydrocarbon chapter, aromatic electrophilic substitution reactions. Here, I'll start from toluene, and my aim is to bring about a chlorination or bromination on the benzene ring. For that, I consider either chlorine or bromine represented as X2. So to bring about chlorination on the benzene ring, the required conditions are I have to make use of halogen carrier like Fe or FeCl3. Reaction has to be carried out in dark, and the reaction must be carried out at room temperature. Under these conditions, CH3 group in toluene is ortho and para directing. That's why in one case the halogen atom enters onto ortho position. In the second case it goes to para position. But in general, between ortho and para isomer being thermodynamically more stable is the major product formed. Now, how are we going to separate these two isomers? There is a considerable difference in the melting points of ortho and para isomers. That's why we can easily separate them by means of difference in their melting point. Now, what about iodination? You have already studied about this. The reaction with iodine is a reversible reaction. Reversible reaction. When you say reversible reaction, what's the problem? At any point of time, you will have reactants as well as products. As a result, yield will be less and obtaining pure product will be difficult. That is why when we want to carry out iodination, I have to ensure that the equilibrium is shifted altogether towards right. So what should I do for that? I have to ensure that one of the products formed is removed as soon as it is formed. Let me explain that by considering a specific example. Last year, you have already studied about it. Here, what I do, I'll start from methane, CH4. I will treat it with, let us say, iodine. What is the product expected? Product is CH3I plus I will get HI. First, I told you the reaction is reversible. So at any point of time, we will have all these substances in the reaction mixture. That's why yield is less. And because you have so many substances, separating pure methyl iodide is not so easy. Now, if I want to drive the equilibrium in the forward direction, I have to remove one of the products as soon as it is formed. So what I do for that, I'll go for oxidizing agents. Oxidizing agents like HNO3. So what happens when you make use of HNO3 is, whatever HI is formed, this HI will undergo oxidation to I2. So when I2 is formed, concentration of HI is reduced, and according to Le-Chatelier's principle, equilibrium will be pushed in the forward direction. So that is a point you are supposed to know. So iodination is reversible. Hence, we need an oxidizing agent like HNO3 or HiO4 to oxidize formed HI to I2. Now, what about fluorocompounds? We can't prepare fluorocompounds by this particular method Because what's the problem with fluorine? Fluorine is highly reactive and it causes the cleavage of carbon-carbon bonds, etc. That's why we do not obtain fluoro compounds by this particular method. So the reason that I have highlighted is it's because of very high reactivity of fluorine. Next, the third method is important one. First, we have to go for diazotization. I'll explain what is it. And that has to be followed by Sandmeyer's reaction. First, let us know what is meant by diazotization reaction. I'll start from aniline. Aniline is actually aromatic primary amine. We have to treat it with nitrous acid. What is nitrous acid? HNO2. We prepare this nitrous acid in situ. How? By considering a mixture of sodium nitrite, NaNO2, with HX. And temperature employed is very, very important here. It has to be 273 Kelvin to 278 Kelvin. For any reason, it cannot exceed 283 Kelvin. Or in other words, reaction has to be carried out in between 0 to 5 degrees Celsius. For any reason, temperature should not exceed 10 degrees Celsius. What happens if it exceeds 10 degrees Celsius? You'll study under subsequent chapter later. For the time being, it is not required. What way reaction takes place? A molecule of water is removed. Here, again, one more molecule of water is removed. What we get is a benzene ring, single bond N, double bond N, single bond X plus 2H2O. So whatever structure I have written is a covalent structure, but what we obtain is a salt. We have to write it in ionic form, and ionic structure will be benzene ring, N plus, triple bond N, single bond X minus, and name of the compound is benzene, N triple bond N, N double bond N actually. It is called diazo group. So it's a benzene diazonium. You have a positive charge on nitrogen. That's why diazonium. Then here it is salt, X minus. It's a salt. So what we get here is aqueous solution of benzene diazonium salt. Generally, we should never try to isolate solid benzene diazonium salt from aqueous solution because it is highly unstable in the solid state and it explodes. So, in diazotization reaction, I repeat, aniline is treated with a mixture of sodium nitrite and HX at 273 to 278 Kelvin. We get an aqueous solution of benzene diazonium salt. The reaction is called diazotization. So this is a very important reaction. Again, you are going to study about that under amines chapter. Now, once you get a freshly prepared aqueous solution of benzene diazonium salt, I will treat it with cuprous halide in presence of HX. What I mean by that? If I consider cuprous chloride, Cu2Cl2, here I have to go for HCl. If I go for cuprous bromide, Cu2Br2, here I have to go for HBr. What happens is, entire diazonium salt group will be replaced by the X group, chloro or bromo. Meanwhile, nitrogen gas is liberated. So by this method, I can get aryl chloride or aryl bromide. So if you consider diazotization with the Sandmeyer's reaction, it is possible to convert, aniline. You can convert aniline into either chlorobenzene or bromobenzene. Now, is it possible to convert it into aryl iodide? It is possible. What we have to do, whatever freshly prepared aqueous solution of benzene diazonium salt we get, we simply need to shake it with potassium iodide. What we get? We will get aryl iodide. Along with that, we get N2 and KX. Next, the next one is starting from alkenes. And all of you are familiar with whatever reactions I'm going to explain now, because in grade 11 you have already studied about this reaction. First one is addition of hydrogen halides to alkenes. Alkene in general is represented like this: C double bond C with two unsatisfied valencies on each carbon, and I'll treat it with HX. So here again, X can be chloro, bromo, or iodo. The product obtained is alkyl halide. Now, if suppose the starting alkene is unsymmetrical, Markovnikov's rule comes into picture and the major product is obtained in accordance with Markovnikov's rule. In order to explain that, I've considered propene. I'll treat it with HI. There are two possibilities. This I can go to the central carbon, hydrogen can go to terminal carbon. So in such case, I'm going to get major product according to Markovnikov's rule. You know, the negative part of the adding species must go to that carbon atom involved in the double bond containing lesser number of hydrogens. That's why, 2-iodopropane is the major product and 1-iodopropane is the minor product. Moving over to the second method, I have to consider addition of halogens. For example, I'll start from ethene. I'm going to treat it with bromine in carbon tetrachloride. What happens? The reddish brown color of bromine in carbon tetrachloride is discharged or decolorized. It is because bromine gets added across C double bond C. What we get here is 1,2 dibromoethane, and it's a vicinal dihalide. All of you are clear about it. And this vicinal dihalide is colorless. And it's for this purpose, this reaction is actually used as a test for unsaturation. You have already studied this in class 11th. Let us consider example 10.4 in NCERT textbook. You have to write the products. See, what they have done here is they have given the reaction. They have given the reaction, you have to guess the product. Right? So, alkene is given and you need to add HBr. So, what way addition takes place? According to Markovnikov's rule. Remember, if they give peroxide here, addition should take place according to anti-Markovnikov's rule. Peroxide is not mentioned, so addition should take place according to Markovnikov's rule. So according to Markovnikov's rule, the negative part, bromo group, should go to that carbon atom involved in the double bond containing lesser number of hydrogens. So you can make out this carbon has only one hydrogen, this carbon has two hydrogens. So it's very clear that the bromo group will go to this carbon atom, double bond becomes single bond, and hydrogen gets added to the terminal carbon. As a result, what's the product that you have to get? The product is this. You can make out bromine atom is added over here and one more hydrogen is added here. So this should be the product. Now, moving over to the second example. Here it is HBr in presence of peroxide, and you know that addition should take place according to anti-Markovnikov's rule or peroxide effect. According to that, bromine atom should go to carbon atom involved in the double bond containing more number of hydrogen atoms. So bromo group will go to terminal carbon and hydrogen goes to the other doubly bonded carbon atom. So what should be the product? The product is, you can make out bromine has gone to terminal carbon, hydrogen has gone to the other doubly bonded carbon atom. That's why this is the product obtained. Once you are familiar with that, next we will go for halogen exchange method. The purpose of halogen exchange method is to convert, alkyl chloride or alkyl bromide into alkyl iodide or alkyl fluoride. For that, first I'll start from a reaction called Finkelstein reaction. The purpose of Finkelstein reaction is to convert an alkyl chloride or alkyl bromide into alkyl iodide. So how do we carry out the reaction? I'll start from alkyl chloride or alkyl bromide. I'm going to treat it with sodium iodide in dry acetone. We get alkyl iodide and sodium halide. Now, why should I go for dry acetone as the solvent? The byproduct formed is sodium chloride or sodium bromide, more ionic in nature. That's why it's insoluble in organic solvent like acetone. That's why NaCl or NaBr will form a precipitate, and that precipitate can be easily filtered off. The concentration of sodium chloride or sodium bromide decreases, and according to Le-Chatelier's principle, to compensate for the decrease in the concentration of NaCl or NaBr, the equilibrium shifts in the forward direction. So that's what I have written over here. Formed NaCl or NaBr precipitates in dry acetone, so we can filter it, and because of that, forward reaction is favored. The next one is Schwartz reaction. What is the purpose of Schwartz reaction? We want to convert, alkyl chloride or alkyl bromide into alkyl fluoride. How do we do it? For example, I start from alkyl bromide, methyl bromide I have considered. I can treat it either with silver fluoride or mercurous fluoride or cobalt fluoride, or I can go for antimony trifluoride. What happens? The bromo group will be replaced by fluoro group. We get methyl fluoride and silver bromide. Now, both the reactions are important. I repeat, from Finkelstein reaction, I can convert alkyl chloride or alkyl bromide into alkyl iodide, whereas from Schwartz reaction, I can convert alkyl chloride or alkyl bromide into alkyl fluoride. Now, the next in-text question we have to consider is 10.3. Write structures of different dihalogen derivatives of propane. So how are we going to do it? Right. So the structure of propane, all of you are familiar. It is CH3, CH2, CH3 is propane. In the first case, I have replaced two hydrogen atoms of the terminal carbon atom by two chloro groups. So I get geminal dihalide here. It's a 1, 1 dichloropropane. In the second case, I have replaced two hydrogen atoms, one from each carbon atom, adjacent carbon atoms. As a result, I have got vicinal dihalide. So name of the product is 1, 2 dichloropropane. Then in the third case, again, I've got geminal dihalide, but in this case, both the chloro groups are present on the central carbon atom. The name of the product is 2,2 dichloropropane, and in the last case I have replaced one hydrogen atom each from the terminal carbon atoms. So I have got 1,3 dichloropropane. Next. The next question is 10.4. Among the isomeric alkanes of C5H12, identify the one that on photochemical chlorination yields a single monochloride. Second sub question, three isomeric monochlorides. And in the third case, four isomeric monochlorides. Four isomeric monochlorides. Right. So when I want to get a single monochloride, what should happen? In that particular hydrocarbon, all the hydrogen atoms must be equivalent. What is meant by equivalent? Consider the structure of neopentane. This molecule is called neopentane. In neopentane, you can observe that there are four methyl groups on the central carbon atom. That's why all these hydrogens are equivalent. So whichever hydrogen you replace by one chloro group, you are going to get the same product. That is why, monochloride, a single monochloride is obtained only when we start from neopentane. Next, I want to get three isomeric monochlorides. That means the isomer of C5H12 must have three different types of hydrogens. So consider the structure of N-pentane. You can make out, you see, these two terminal hydrogen atoms are identical, and then the second carbon atoms from either side will have identical hydrogens represented as B, and the central carbon will have another type of hydrogen. So altogether, how many types of hydrogens we have here? Three types indicated as A, B, and C. Correspondingly, we'll have three isomeric monochlorides. Then the next one, I have to get four isomeric monochlorides. That means there must be four different hydrogen atoms. For that, I'll consider the example of isopentane. So in isopentane, you can make out, you see, these two hydrogen atoms are equivalent, A, different one B, this is different C, and the terminal one again is different, it is D. So how many types of hydrogens we have? Four types. That's why I'm going to get four isomeric monochlorides. Next, draw the structures of major monohalo products. So in this question, right, let's consider the reactants that are given. It's a cyclohexanol, and I'm making use of SOCl2, right? So what is the role of SOCl2? You have studied in Darjan's process. We can replace the OH group by Cl group. So what is the product obtained then? This OH has to be replaced by Cl. That's why the product that we are going to get is chlorocyclohexane. Let's go for the second one. In the second case, we make use of bromine. We are going to heat it or UV. When we heat it or when we make use of UV, free radical substitution reaction takes place. Now the question here is, which is the most stable free radical that is formed? So in order to understand that, let me explain this concept. You have a benzene ring here and you have NO2. In this case, This carbon atom is called benzylic carbon atom. And in class 11th, you have already studied that benzyl free radical is the most stable one. That's why you have CH here, and then you have CH3, and this CH2, I'll represent it like this. Now, if this carbon hydrogen bond undergoes homolysis, so we get a very stable benzyl free radical. I'll represent it like this. It is a CH, then it is CH3. You know that this is the most stable benzyl free radical, most stable benzyl free radical. Now, this benzyl free radical now will combine with bromine free radical. As a result, what's the product that we have to get? So, bromine free radical gets attached over here. That's why the major product obtained here is this. So, bromine atom is connected to benzylic carbon. Right. So, next, we will consider third question. In the third question, right, so this is a reaction what they have given, right? So you are using HCl. Now the question is whether this HCl can replace a OH of CH2OH and also OH directly connected to benzene ring. Answer is, HCl can replace only OH connected to an alkyl group, but it cannot replace phenolic OH, we say. OH, which is directly connected to benzene ring, is a phenolic OH. And very shortly, you are going to study that the bond between carbon atom of the benzene ring and oxygen atom of OH has a partial double bond character due to resonance. That's why breaking carbon oxygen bond in case of aryl oxygen case is difficult. So HCl cannot replace phenolic OH. It can replace only OH attached to alkyl group. That's why what will be the product? Simple. Only this OH will be replaced by HCl. Only this OH is replaced by Cl. So the product is CH2Cl. This OH remains intact. Next, I'll move over to fourth example. Here you have a CH3 group on cyclohexene, right? I'm going to carry out addition reaction with HI. Markovnikov's addition rule comes into picture. Obviously, this iodo group, iodine atom, should go to that carbon atom involved in the double bond containing lesser number of hydrogen atoms. So iodine gets added to this carbon, hydrogen will go to this carbon. The product obtained is this. And finally, if I consider this example, here bromination, you are heating and then UV light here. It's a free radical substitution reaction. We call it as allylic bromination. So if you want to know how exactly the reaction takes place, it is this way. You have a double bond over here. You have a double bond, right? So here you have hydrogen, here you have hydrogen. So this is allylic carbon, and this is also allylic carbon. And you know that allylic free radical is more stable. So what I do, I'm going to go for homolysis of CH bond of allylic carbon. So this results in the formation of a more stable allylic free radical. So I can represent it this way. Now, next, what should happen? This is a allylic free radical, and allylic free radical is more stable. So that's why the bromine free radical goes and attaches to this carbon. So what should be the product? In the product, you should have cyclohexene structure, and in the allylic position, bromine atom must get attached. So that's what I have shown here. Bromine atom is attached over here. This is the product.